Let's graph the feasible region for this system of inequalities. We're going to start by graphing all the lines, and we will do that by finding x and y intercepts. I'm going to think of setting the x value equal to 0 in this first inequality. That means I can cover up the x because that first term will disappear, which puts my y at 20. Now we think of setting my y equal to 0. So you can just cover up that term. That gives me 5x equals 20, thinking of the associated equation, and that gives me an x value of 4. Let's move to the next one. We're going to set the x equal to 0. That gives me a y value of 12. Now we think of setting the y equal to 12. Setting the y equal to 0. So I can think of this y term as going away, which gives me an x of 12. Now move to the third equation. My x is 0. Setting x equal to 0 to find the y-intercept. So we think of this term as disappearing. That gives me 3y equals 18, so y is 6. Now we think of setting the y equal to 0. So now we get an x-intercept of 18. So just like that, we have a bunch of ordered pairs here. If we move to the last two inequalities, notice what these are really saying is that x and y are not allowed to be negative. What quadrant does that put us in? It puts us in the first quadrant. So this is just another way of saying that our feasible region is entirely contained in quadrant 1. We don't have to worry about the other quadrants. We call these non-negative inequalities. Okay, so let's graph these. The reason I find all of the x and y intercepts before I start to graph is that I want to look at all of them before I choose my scale. I know that my y needs to go up to 20, my x needs to go to 18, so I think it will be a good idea to choose a scale of 2 units to 1 tick mark for both axes. You don't have to choose the same for both, it's just in this case it happened to be convenient. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Here we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And I'm not concerned with the negative numbers. So now I need to graph my lines. So we start with the first one. So we need to go up to 0, 20. Hang on, it looks like I wrote 0, 26 there for some reason. Let's make that a 20. 0, 20, and then 4, 0. So I draw a line through here. You will want to use a straight edge to make sure that your lines all intersect properly. Sometimes you can really mess yourself up by going just a little bit crooked with your line. Once you get it graphed, you want to make sure that you label it. So I'm going to label this as 5x plus y equals 20. Now I've moved to my second line, x plus y equals 12, so both my x and my y-intercepts are 12. I take my straight edge and I draw my line. And I label it. And now we do the third line. So 0, 6, 18, 0. Okay, notice all of these are solid lines because we do not have any strict inequalities here. All of these, in all of our inequalities, the equation is included as well, and so we do not have any dashed lines. I should have mentioned that before. So now we need to do our inequalities. For all of them, let's use our test point of 0, 0. because it's not in any of the lines, so I can do that. You do not need to use the same test point for all of them, but I'm going to use 0, 0 unless I can't. Okay, so if we look at the first one, that's going to give me 5 times 0 plus 0 less than or equal to 20. So 0 less than or equal to 20, which is a true statement. And that tells me that I want to shade toward 0, 0. In other words, I want 0, 0 to be shaded. And with 3, once you start to get 3 lines, it starts to get a bit confusing if you shade all over your paper. Unless you use different colors. So let's just indicate our shading direction with arrows. So I'm going to shade this one toward the origin. We'll eventually shade only our final region. Okay, so that one gets shaded toward 0, 0. Now we move to our second line. When I put in 0, 0, that's going to give me 0 less than or equal to 12, which is true. And so once again we shade toward 0, 0. Here's where you'll be glad you labeled your lines. You can keep track of which one is which, so you draw your arrows attached to the correct lines, which is good. And now let's move to our third line. This one gives me 0 greater than or equal to 18. That's a false statement. And so that tells me that I'm going to shade away from 0, 0. So this one gets shaded away from 0, 0. Okay, and so now you need to figure out which area satisfies all of your inequalities. And sometimes you can do it just by thinking of one and asking yourself if it works. Like if I look at this area, this satisfies one of my inequalities. It satisfies the x plus y equals 12 shading, but it doesn't satisfy either of the other two. If I come over here, this doesn't satisfy any of them. If I look at this little area in here near the origin, it satisfies 2 of them, but it doesn't satisfy the x plus 3y equals 18. Okay, so what area satisfies all of them? If I come here, this satisfies 2 of them, but not the x plus y equals 12. But what about right here? This little area, remember we're only talking about areas that are in the first quadrant because of that x greater than or equal to 0, y greater than or equal to 0 that's at the end. Looks to me like this area will satisfy all of them. So that's the one that I want to shade. Okay, so we're going to shade this area right in here. Okay. And now we want to find our corner points. So where are they? There are 4, right? Now the ones that are on the axes should be obvious. So if we're starting to make a list of corner points, there are 2 that we can write in right away. Okay, we know that we have 0, 12, and we know that we have 0, 6. Do you see where I'm getting those? Right here and right here, because I know where those y-intercepts are, and so I can just write them down. Now the other 2, right here and right here, we're going to have to do a little bit of algebra to find those. Here's where again you will be glad that you labeled your lines, because you want to do substitution and elimination to determine where those lines cross. and you'll need to know which lines to intersect. Okay, so for one of them I need 5x plus y equals 20, and I also need x plus 3y equals 18. That's this point right here. Okay, so let's do elimination on these. I usually find that to be quickest, so I'm going to multiply my first one by -3. That gives me negative 15x minus 3y equals negative 60. Then when I add these, now I have negative 14x, negative 42, and so my x is 3. Stick that into one or the other of your equations. So 5 times 3 plus y equals 20. So y is 20 minus 15, which is 5. So that's one of my corner points. I can add it to my list. Before you go on, look to see if that seems reasonable based on your graph. Looks okay to me. That looks like about 3 to 5. 3,5 rather. Now we need to go to our next one. And so for this one, looks like we need 5x plus y equals 20, and we also need x plus y equals 12. So 5x plus y equals 20. X plus y equals 12. If you want, you can just subtract the equations right here. What will that give me? 4x, y minus y is 0. 20 minus 12 is 8. And so now my x is 2. Put that into one of your equations. If you do x plus y equals 12, put that in. And so my y is 10. And so once again, you look on your graph to see if that seems reasonable. I think that looks reasonable. So we're going to write that down in our list of corner points. So our feasible region is shaded clearly, and now we have our corner points. The example that we just did is an example of a bounded solution region. A bounded solution region is one that can be enclosed in a circle. And an unbounded region is one that cannot be enclosed in a circle. And so let's just do a quick example here. Let's suppose, okay, there's a line. And here's another line. And let's say we have a line that looks like this. And let's suppose that our region turned out to be this area. Okay, well, we can enclose that in a circle, and so this is an example of a bounded region. And now let's suppose that we had something that looked like this. Here's a line. Okay, let's say these are some lines, and let's say it turned out that our feasible region was everything like this. Okay, and of course those lines keep going infinitely far, and if we don't have any more boundaries, so will our solution region. We cannot enclose this in a circle because it's going to extend infinitely far in that direction. So this is an unbounded region. Sorry about that. Okay, let's do another example. Let's suppose that we have Budget Cat Food Company, which supplies 2 distributors. One of them needs at least 200 boxes of cat food each month. The other needs at least 400. Limitations of the cat food plant allow us to make 800 boxes at the most. And we want to write a system of inequalities to describe the situation, and we want to graph the feasible region. Okay, the first thing we want to do is we want to figure out what x and y are going to represent. And we don't have names for our distributors, so let's call this one distributor A. And let's say this one that needs 400, we're going to call this distributor B. So we're going to let x be the number of boxes for distributor A, and we're going to let y be the number of boxes for distributor B. So to write a system of inequalities that describes it, looks to me like x, the number for distributor A, needs to be at least 200. The other needs at least 400, so that's B. So that means y has to be at least 400. Okay, now let's look at the production limitation. Budget Cat Food can make 800 boxes at the most. In other words, we can't make any more than 800. And there aren't any other distributors besides these 2. So what does that mean? The number for A plus the number for B cannot exceed 800. What about negatives? Does it make any sense for the number of boxes for distributor A to be negative? No. Same with B. That tells us that x has to be greater than or equal to 0, and y has to be greater than or equal to 0. So here is our system of inequalities. Now let's graph this region. We need to choose our scale carefully. Let's do 1 tick mark for 100 boxes. So 100, 200, 400, etc. Here 100, 200, 400, etc. X greater than or equal to 200. So what does that mean? If x is greater than or equal to 200, so here's the line x equals 200. It's going to be a vertical line. This is the line x equals 200. And what's going to be shaded over there? Everything to the right. So x has to be at least 200. Let's move to the next one. Y has to be at least 400. Well, if I do y equals 400, gives me a horizontal line right here. My problem says that y has to be at least 400, so it could be bigger, but it can't be smaller. That means I'm going to shade up. Now my total has to be less than or equal to 800. Okay, so if I find my x and y intercepts, that means that if I put in x equals 0, my y will be 800. If I put in y equals 0, my x will also be 800. Okay, so 400, 600, 800, that puts me right here on my y-axis. One, 2, 3, 4, 5, 600, and then here's 800 on my x-axis, and now we want to draw the line using those intercepts right here. And which way must that be shaded? Well, we know that if we put in 0, 0, then that gives me 0 less than or equal to 800, which is a true statement, which means we are going to shade toward 0, 0 because we want to include it, so we're going to shade this way. And so now if I look at what area satisfies all of them, it looks to me like this middle little triangle will satisfy all of them. Okay, there's my feasible region. Now if we were to find the corner points, those are easy too. Because anywhere I'm on this vertical line, my x is 200. And then if we put that into our x plus y equals 800, what do we get? My y is 600. So that means this point right here is 200, 600. Okay, if I do y equals 400 and I put that one into x plus y equals 800, what do I get? I get an x of 400. So this point right here is 400. 400. We should already know this one. If we just look carefully, we know this one, my x is 200 and my y is 400. So there are my corner points. So we have our 200, 600, 200, 400, and 400, 400.